Welcome to The Explainer. Today, we're going to dive into something called mathematical series. And trust me, it's way more interesting than it sounds. This is a tool that can help you do everything from planning your finances to, believe it or not, understanding infinity.
All right, let's kick things off with a real-world puzzle. Let's say you're saving up for a college fund. You decide to put away $50 a month every single month for 6 years. So the big question is, at the end of those 6 years, how much money are you actually looking at?
Now, your first instinct might be to just, multiply $50 by 72 months. Simple, right? But wait, if you do that, you're missing out on the most powerful force in finance, interest. It's that magic where your money starts making its own money, and then that money starts making even more. To get the real answer, we've got to track how every single one of those 72 payments grows over time.
So, what seems like a simple money question is actually a math problem hiding in plain sight. And the key, the secret weapon to solving it, is this awesome concept called a mathematical series. So what in the world is a series? Well, think of it like this. A sequence is just a list of numbers, right? Like a list of ingredients. A series is what you get when you actually add all those numbers up. It's the finished product, the final sum of all the pieces.
Okay, adding a few numbers together, no big deal. But adding up 72 different growing values from our savings plan? That sounds incredibly boring and super tedious. But don't worry, mathematicians, being the clever people they are, came up with a really elegant shortcut for this exact problem.
I mean, just look at this. If we tried to write out the whole calculation for our savings plan, it would be this long, clunky mess. Each one of these things represents a $50 deposit plus all the interest it's earned. You can just see how easy it would be to make a mistake or just get totally lost.
And this is where our shortcut saves the day. It's called summation notation, and it uses this cool-looking Greek letter sigma. You can basically think of sigma as a powerful summation machine. It takes that long, messy equation we just saw and cleans it up into one neat, tidy package.
So how does this machine work? Well, the sigma symbol itself just means add everything up. Then you have an index, which is kind of like your counter. The numbers on the top and bottom tell the machine where to start counting and where to stop. And finally, you've got the formula, which is the rule for what numbers to add. It's basically a perfect, super compact recipe for getting a sum.
Okay, so not all series are the same. They actually describe different ways that things can grow. Let's check out the two main flavors you're going to run into.
So on one hand, you've got arithmetic series. This is that steady, predictable growth where you're just adding the same amount over and over. We call it stair-step growth, just one step at a time. But then you have geometric series. This is where you multiply by the same number each time. And this is that snowball growth we were talking about. It starts small, but it picks up speed and gets huge fast. It's all about compounding. For that steady stair-step kind of growth, there's a really simple formula to find the total. All you need is how many steps you're taking, where you started, and where you ended. Super straightforward.
And for that crazy, explosive snowball growth, we've got this powerhouse of a formula. Yeah, it looks a little more intimidating, I know. But this is the one that handles compounding. And guess what? This is exactly the tool we need to solve our college savings puzzle.
Okay, we've got the theory, we've got the tools. Let's circle back to our original puzzle and actually put this stuff to work.
You know this whole savings plan we've been talking about? It actually has a fancy financial name. An annuity. And it's super common. You see this kind of thing everywhere, from retirement plans to car loans and mortgages. All right, let's plug our numbers into that geometric series formula. Our first payment, A1, that's our $50. The number of payments, N, is 72, because it's 6 years times 12 months. And the common ratio, R, that's 1.005. That number represents our money plus the little bit of interest it earns each month.
From here on out, it's actually pretty simple. We just take that formula, pop in the numbers we just figured out, and then it's just a little bit of calculator work. And boom, there's our answer. This is the power of compounding in action. After those 6 years, the grand total in the account is $4,320.44.
So let's break that down. This chart makes it super clear. You put in a total of $3,600 of your own money. That extra $720, that's pure profit. That's money that your money earned all by itself. That is the magic of a geometric series at work in the real world. Okay, so we figured out how to add up a set number of things. But now, let's get a little weird with it.
let's push the limits and ask a really mind-bending question. Here it is. Can you add an infinite list of numbers together and not get infinity? I mean, that sounds like a total paradox, right? If you just keep adding and adding forever, shouldn't the number just get bigger and bigger forever? It sounds impossible, but believe it or not, sometimes the answer is yes, you can.
To wrap your head around this, just think about a simple repeating decimal, like 1/3, which is 0.333 and on forever. You can actually write that out as an infinite sum. It's just 0.3 plus 0.03 plus 0.003, and you just keep going like that forever.
Now here's the secret. The absolute key to this whole thing is right here. For an infinite geometric series to actually add up to a real number, that common ratio, r, has to be a fraction somewhere between -1 and 1. Why? Because that means every new number you add is smaller than the one before it. The pieces you're adding keep shrinking, getting closer and closer to 0, so the total sum hones in on one specific final value.
And what's really wild is that the formula for this is just shockingly simple. To find the sum of one of these infinite series, all you do is take the very first number and divide it by 1 minus that common ratio. That's it. You have an infinite problem with a beautifully simple, finite answer. How cool is that?
So whether we're talking about saving for college or trying to wrap our heads around the idea of infinity, these mathematical series give us this really elegant language to describe how things grow and change all around us. And it really makes you wonder, right? What other things that seem totally impossible right now are just waiting for us to find the right tool to understand them?